where are we?
We just got done with amides.
Finished it, right? Yeah.
We did some
Thank you, Mark.
We did some examples.
So did we finish amides? Yeah. Okay. So we finished that chapter. And I said I'm going to actually combine. Sorry, I'm chewing at the same time. I'm so sorry.
No, you're
Probably
fine.
have food in my teeth. So we are going to combine the next two chapters. Is that something I said?
The next chapters
22 and 23 we are going to look at, because their reactions are very similar, the thought processes are very similar. So that's how I'm going to do. So let's get started. In this chapter, we are going to look at aldehydes and ketones and esters again, with one difference. When we looked at aldehydes and ketones and esters so far, and their reactions, we basically saw how a nucleophile can come in and attack. Isn't that right?
Yep.
And that's kind of what we did for all reactions. That's what we did, right? In these two chapters, though, we are going to look at these three families, but from a different perspective. Please tell me, if you remember, a nucleophile, is it electron rich or electron poor?
Electron rich.
So anything that's electron rich can be a nucleophile or be a
base.
That's the part we are going to look at. Okay, what if whatever is a nucleophile actually decides not to act as a nucleophile, which means it should go there? What if it decides to act as a base? Then what? And that's the focus of the next two chapters. So we are now looking at aldehydes and ketones, but we are looking at aldehydes and ketones that have, whatever that is, that have at least one or more hydrogens on the alpha carbon. So this is the alpha carbon. Right next to C double bond O is the alpha carbon. The hydrogen on the alpha carbon is decently acidic. It's not very acidic, but I think the pKa, and I'm trying to remember what the pKa's of these are, and I can't remember on the top of my head. 20, okay, that's what I was thinking. Aldehydes and ketones, it is 20-ish around. For esters, it's about 35. So not too acidic. This is for aldehydes and ketones. For esters, it's around 35. So they're not too acidic, but if you have a base that's strong enough to deprotonate, then we can take that proton out. Now, let's say, if I ask you, what would it create if there were a base, whatever the base is, we'll discuss all of that as we go. If the base were to come in, instead of acting as a nucleophile, if it were to take this proton, what will it create? Anybody? What will it make?
An alpha carbocation?
Cation.
Anion.
A carbon.
Right? Those electrons will have to go in.
Carb anion, that's right.
So what is so special about this carb anion?
Resonance.
What is the resonance structure of this anion? Isn't that right?
Oh.
Agreed?
Yep.
So these are resonance structures, and as we've said so many times, resonance structures don't exist. What exists is the hybrid of the two. But the point is, what does this remind us of?
Like an alkoxide, or do you
Yeah, sure, but it's also a double, it's on the alkene.
Oh.
If I put a hydrogen there, just as to remind you, what is, okay, you tell me.
It makes an enol?
Good, so what is the conjugate acid of this guy?
An enol.
If this were to take a proton, what would it become?
An enol.
Enol, do you all agree?
Mhm.
Everybody okay? We've seen enols before, isn't that right?
Yeah.
So can you tell me what would be the name given to the conjugate base of the enol? Just take a wild guess. That's the acid, this is the base. So the enol, base of the enol would be called?
Enoxide.
Okay, well maybe that's a reasonable guess, but not quite. Say again? But that's the acid, this is the base. No. Enol, if it gives away a proton, what does it become?
Enolate. Okay.
Isn't the 8 for
Say that again?
esters?
Yes, exactly. That's where it comes from because, for example, ethyl acetate and so on and so forth, because that's the conjugate base portion of the carboxylic acid. So the point is, these two chapters are basically going to deal with enols and enolates. Enols and enolates, which causes the alpha carbon to become electron rich. And we'll see that as we go through different reactions. Everything is now going to happen on the alpha carbon as opposed to the electrophilic C double bond O reactions would happen on the alpha carbon. Sounds okay, everybody, so far? Okay, so then let's start with something that we have seen before, and that is keto-enol tautomerism. Do you guys remember keto-enol tautomerism?
Yes.
Yes, in which context was that? Reaction?
Alkyne.
Alkynes being hydrated, right?
Mhm.
Okay, so this is, and I don't know if we wrote a mechanism for keto-enol tautomerism
We
then
did.
or not,
Yes.
but let's do it again.
Like acid and base.
Yes, exactly, exactly. Acid catalyzed as well as base catalyzed. So let's take an example. Please tell me what will be the enol form of cyclohexanone. Can you tell me what will be the enol form of this guy?
Mm.
So how do you figure that out? The way you figure it out, one of the hydrogens from alpha carbons, of course there are two alpha carbons here, but they are the same, agree? Because it's symmetrical. So can I just look at one of them and explain? Of course, if it is not symmetrical, then you'll get different enols. But in this example, because it's symmetrical, the two alphas are the same. So one of the hydrogens from the alpha carbon, again, this is not the mechanism, I'm just showing you what's going on. One of the hydrogens from the alpha carbon goes to the oxygen. So the oxygen takes one of those hydrogens, and then the electrons go here and that sort of. Does that make sense, everyone? In terms of what's going on, what is moving where? So if you think about it that way, that okay, one of the H's from the alpha carbon is going to move to the oxygen, and therefore the pi bond is going to shift, what is the enol form for this ketone?
OH, I mean,
Uh-huh.
I don't know the name.
But then, what else?
A double
Double
bond.
bond.
Right there.
Cyclohexanol.
Exactly. So that's the enol form, this is the keto form. And yes, this reaction is reversible. Does anybody remember, typically speaking, which form is more stable?
Keto
form is typically speaking more stable compared to the enol form. So at equilibrium, the keto form is the major form, enol form is the minor form. But this reaction can either be, this tautomerism can either happen in presence of an acid or in a dilute base, either in a dilute acid or a dilute base. So let's write a mechanism for both of those, dilute acid as well as dilute base, to understand how the keto-enol tautomerism is happening, okay? Let's start with acid catalyzed process. Can someone tell me what will be the first step for the acid catalyzed?
Protonate.
Protonate what?
Oh,
The double bonded O gets
Yeah.
protonated.
Do you all agree? Okay. What will that do?
Plus
Uh-huh.
OH.
Okay, then what?
Then we OH into the electrophile.
Yeah,
Carbon
but,
electrophile. No?
you're right. This is electrophile, but we're not adding any nucleophile, right?
Oh no.
Mm-hmm.
There's no nucleophile coming in.
One of the bonds breaks and goes to the
Say that again, Jasmine.
One of the bonds of the double bond breaks and goes to the opposite.
Okay, but isn't that just a resonance structure?
Oh,
Those are
yeah.
resonance structures of each other. Okay, I mean, sure, that's fine. We can write that. Is this what you mean? Yeah? Yeah, those are resonance of each other. Okay, what next? Louder? Of what? Are
Oh,
we eliminating anything
a hydrogen goes off
from
from the alpha carbon,
as a what?
proton.
Proton. It's acid catalyzed. We took a proton, we are needing to create a proton. So one of the protons or hydrogens from the alpha carbon is going to be lost as a proton.
Oh.
Who's, in this case, who's taking the proton?
Water.
Because I used H3O plus, I'm going to create H3O plus, takes it from here, creates the double bond, giving us the enol form. Of course, all these steps are reversible because this process is reversible. The point is protonate and then deprotonate from the alpha. Gives us the enol form. Do you all see that?
Mhm.
Okay, let's write the base catalyzed keto enol tautomerism. What should be the first step?
Base attack.
Exactly. No nucleophile here, base. So who's the base here in this example?
OH minus.
So what is it doing? What is the base doing?
It's taking a proton.
From where? Exactly. It's taking a proton from the alpha carbon. What would that create?
Okay.
Carbon ion?
Yeah.
Isn't that right?
Mhm.
What is a carbon ion which is conjugated to the double bond? It's an enolate.
Mm-hmm.
Can I write it this way, guys? Again, it's a personal preference. How about this? And write the other resonance structure, the enol. So instead of showing this carbon ion, can I just go directly here? The answer is why not? Because resonance structures anyways don't exist.
Mhm.
So the point is it creates an enolate ion. Agreed?
Mm-hmm.
Then what? Where, say that again, please.
It reacts with water in the environment
To create, what does water do?
it protonates the.
Water acts as an acid because that's a strong base. Water can give a proton and create the enol and recreate the base because it's catalytic in hydroxide. Exactly. If it's an acid catalyzed ketonol tautomerism, protonate first, deprotonate next, you get the enol. If it's a base catalyzed process, deprotonate from the alpha position first, protonate, you get the enol. Does that make sense, everybody? Yes? So this is keto enol tautomerism. Let's try a couple of more times. What I need you to do is, for these ones that I'm going to write on the board, basically, oh, by the way, before I go forward, in an acidic environment, when this is happening in presence of an acid, do we get an enolate at all?
No, you don't.
Enolate is created only in the base environment. Agreed? Everybody? Because enolate is negative. Negative can exist only in basic environment, not in acidic environment. Okay, so draw either the enol form or the enolate form for each of these substances. Again. So which form will exist in acidic environment? Enol or enolate?
Enol.
right? What will exist in the basic environment? Enolate. That's basically the idea. Yes, absolutely. Let's draw, please, whichever should be valid form depending on the conditions. So in an acidic environment, you will have the enol form present. In the basic environment, there will be enolate. So what we are asking here is for you to draw the enol form or the enolate form, whichever would exist given the condition. Please feel free to draw those out.
That's right. Carbon's making 4 bonds. Is that good? That's good. No. Let's see what Samita has to say.
What happened? Did I do something wrong?
No.
Do I put the H or?
Does it exist?
Yes.
Because
I
the
could leave it
base,
like that, right?
oh, you can, but so does it exist though? Even if you leave it like that, is it still there?
Yeah.
Yes, it's as long as you know that that's still there. Because the base didn't take this proton, the base took that proton. Isn't that right?
Yeah.
So it still exists. though.
Yeah.
One at a time. Was it you, Dash? Or was it, who did this one?
I did that one.
One at a time.
Okay.
Not both.
one at a time.
That's all.
So what would it be then? Oh, did you do that? Who,
No,
I did that.
Dash did? Yeah, so not both sides at the same
I
time.
figured because it was resonance structure, it was kind of.
Yeah, but that's not part of resonance structure. Because you have an sp3 hybridized
They
carbon,
both
right?
have thermal resonance, so it's not either one.
So this is separate from that, isn't that right? So you either will have one side or the other, but not both sides. You can't. What happened, Carter? Are you still figuring this one out? I thought you were writing this.
You were gonna do it?
That's okay, someone else can too.
Yeah. That was what I was gonna leave.
That's
it
okay.
for.
Does anybody have the answer for the last one? exactly the same thing where the alpha carbon loses a proton and gives us the enolate or the enol, depending on whether it's in acidic conditions or basic conditions. But do you all agree? Right? Everybody okay? So it's the alpha carbon that has a hydrogen. This one does not have a hydrogen, so you can't do it. So acidic gives you enol, basic gives you enolate. Of course, the enolate can be protonated and blah, 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 but you have that. Now this one is the one I was saying to Dash earlier, one at a time. You can't have both sides being deprotonated. So I would keep one unchanged and the other one loses a proton, let's say. Agreed? I think what you're trying to say here, Mar, is that a negative charge, right?
Yes.
Okay,
Oh, because it looks like that.
or at least on the top, because charges are always superscripts. Charges are never written under, they're written. So just to keep it clear.
Okay.
But you're absolutely right. And then, everybody okay?
Yeah.
Everyone okay?
Mm-hmm.
Cool, so then let's look at our first reaction using enols or enolates, depending on the conditions, whether it's being done. Oh, actually, no, before that, before we can go forward with that. Sorry, yeah.
So the second one on the lower left, like, could that form two products?
Lower left, this side?
No,
The one that dash.
The one that
Dash.
one of the ones that dashed it, yeah.
Yes, but it's symmetrical.
But it's the
Oh.
same one, right?
Symmetrical,
Oh.
so same. Right, if it weren't symmetrical, then yes, the answer, and actually I'm going there too. But you're right, if it weren't symmetrical, then yes, you could have two different ones. Absolutely right.
Yeah, but still you do one first and then.
Or the other, yes, absolutely.
So it would be one plus the other.
Yes, exactly. Okay, okay, why don't you guys tell me, because that question came up just now. How many enolates, different enolates can I get from that? How many different enolates? Two. Because there are two different, this is not symmetrical, right? That's what you were asking. There is alpha hydrogen here, which is totally different from the alpha hydrogens on the other side, right? So yes, it can create two different enolates. So we're going to talk about now the choice of base. Is there a way for us to make one enolate the major enolate or the minor enolate, depending on the structure of the molecule? The answer is yes, we can. So one of the enolates possible would be, do you agree? Yes? And the other enolate possible would be that one. Agreed?
For enolate.
Enolate, because we're talking about base, so it has to be an enolate. Agreed?
Mm-hmm.
Now, can you tell me, just looking at the enolates, can you tell me which enolate is more stable? Which enolate would you expect to be more stable and why? Do you all agree? The more substituted double bond, remember the alkene stabilities, the more groups on the alkene, the more stable it is.
Yep.
So this is more stable double bond compared to that double bond. Everybody okay with that part? So this is called the thermodynamic enolate. Why? Because it is the more stable. Now, in order to create the thermodynamic enolate, we had to remove this hydrogen, agreed?
Yep.
But in order to create the other enolate, we would have to remove one of these blue hydrogens, or the black, am I right?
Yeah.
Can you please tell me which proton, the red or the black, is easier for the base to get to? All H's. I mean, right? Your Dash is saying the black one. Why though? Steerix, exactly. Exactly.
Steerix.
So if you have a base that is bulky, and we will go over some of those choices, it's easier for it to take this proton than that because this is more accessible. That's all about steerix. So therefore, the activation energy, the energy of activation to create this enolate is actually lower. This creates faster, but this one is more stable. So we call this one the kinetic enolate, because the activation energy to produce this one is smaller, because it's easier to grab that, because that is more open, available, not crowded. Everybody okay? So the thermodynamic enolate is the more stable enolate, but the kinetic enolate is the one that's coming from the taking away of the more open hydrogen, alpha hydrogen. So how do we decide which base to use to get either the thermodynamic enolate or the kinetic enolate, depending on what we want to do? So generally speaking, the thermodynamic enolate, it can be created with bases such as hydroxides or alkoxides. But of course, T-butyl is very bulky. Remember, this is not for T-butyl. Not, because T-butyl is very bulky. The problem though is that these are not very basic. These are weak in the big scheme of things. They're not very strong bases. So they unfortunately end up giving us an equilibrium process where you just have to deal with it. You have to figure out what do you do, because the bases are not that strong. On the other hand, kinetic enolate, if we want, we would use a bulky base. So I'm introducing a new base to you, which is only used for these reactions. This base is called LDA. LDA stands for, L stands for lithium, as you would imagine. D stands for diisopropyl, and A stands for LDA. It's a very strong base, but also, or rather, there's no but here. It's a very strong base and also a bulky base. Lithium is only a counter ion. It really doesn't do anything except to balance out the charges. The actual base is the diisopropyl amide. It's very strong and bulky. If it's very strong base, which means there's no equilibrium, it just goes all the direction of the enolate, because it's a strong base, it just takes a proton. But because it's bulky, it favors the kinetic enolate, not the thermodynamic. So LDA is a base that you will actually come across quite a bit in these two chapters. And every time LDA is used, please remember, it's a strong base, which means there's no equilibrium here. The reaction essentially goes all the way to the enolate. And it's bulky, so kinetic enolate is favored if there's a choice. Everybody okay? Yes? Cool. Okay, then let's go ahead and look at some reactions using enols and enolates. Maybe I should start from here. The first one we will talk about, there are several ones we'll talk about, and soon enough you'll start seeing a pattern, soon enough. The first one we'll talk about is alpha halogenation of aldehydes and ketones. Only aldehydes and ketones, not esters, please note. Okay, so basically, if I have an aldehyde or a ketone which has an alpha hydrogen, so we remember this reaction is all about using the alpha hydrogens. So we definitely need to have at least one, if not more. We definitely need to have that. If I were to react this, either halogen in presence of an acid or halogen in presence of a base, that will convert this into an alpha halogenated aldehyde or ketone. ketone. So the note, the reaction is not on the C double bond O, the reaction is on the alpha position. If the reaction is on the alpha position, we have to think about enols or enolates. That's the only way we can get something on the alpha position. Everybody okay? Let's look at an
We do
example.
have two H's over here, right?
Yes, I just deleted one because the focus is one. But of course, yes, there has to be one.
It
There
could
has
be
to
an R or it could be an H.
It could be whatever.
Okay.
As long as there's one hydrogen on the
Okay.
alpha position. Okay, so let's look at an example, then we'll write a mechanism and see if that makes sense more. Please go ahead, write the product, and I'll write one more here. Okay. Product first. What do you guys think?
For the first one,
Mm-hmm.
it would be 2-bromocyclopentanone.
Everybody okay? Let's write a mechanism. So first of all, you have to decide, will it go through an enol or enolate? Why? Because there's an acid. Exactly. So when you're writing the mechanism, we have to first create the enol. How is the enol going to be created from here? Anybody? What's the first step? Protonate.
Protonate.
That's our first step. Once you protonate, what do you think will need to happen next to create an enol?
Find the H.
Find the H? What did you mean by that?
Well, I
You
mean,
have to use water to take the H.
One
So
of the-
somebody, since I used H plus, I'm just going to do H plus, but someone has to take one of the H's from the alpha position, isn't that right?
Yep.
So basically, then creates an enol. So make an enol because it's in under acidic conditions. Everybody okay? Once the enol is created, this is where the electrophile comes in, not nucleophile. What's our electrophile? That's the halogen. How? Fix it up. So it's the alpha carbon that gets activated. Alpha carbon becomes the electrophile, becomes the nucleophile and reacts with the electrophile. So what will that create? Agreed? Now what? What do you think needs to happen next?
Oxygen ditches its proton, gets rid of its proton.
And creates the product. The point is, you have to show the enol before the electrophile can come in, because it's in interacidic conditions. What's the product here? Now, there are two alpha carbons, but this alpha carbon has no hydrogens. Only one, the other one does. So, the product. Agreed? Okay, let's write the mechanism. Is this going to go through an enol intermediate or an enolate intermediate?
Enolate.
Because there is a,
Base.
so what is the base going to do to make the enolate? Take one of the alpha protons. Now, as I said earlier, you can show either resonance structures. You can either show the carb anion resonance structure, or you can show the enolate resonance structure. This is an enolate. Either is okay, they're resonance structures of each other, neither exists. What exists is the hybrid. Now, generally people tend to show the enolate resonance structure. Any guesses as to why the enolate resonance structure is what people generally show instead of this one?
Because you usually see a negative charge oxygen more.
So,
More stable?
why? Because, exactly. So connect those two dots right there.
Because what?
So this is more stable of the two because oxygen has a negative charge as opposed to carbon having the negative charge.
Oh.
Remember the resonance structure stability octet rule is the first thing we try to look for, but all atoms have octets here, so that's not a problem. Then it's the charge distribution and who has the charge and so on and so forth. So absolutely, most of the times when you go through your books and all, you will see people writing this resonance structure because it's the more stable resonance structure. But if you wrote this one, is it wrong? The answer is no. These are resonance structures of each other which don't actually exist. What exists is the hybrid, so who cares? Okay, and once the enolate has been produced, so you actually have to show the enolate. Once the enolate has been produced, this is when, oh, not Br, Cl. This is where the halogen comes in. So once again, if I'm using that resonance structure, those electrons come back, kick out the chloride, gives us the product. So once again, if the reaction is under acidic conditions, you must show the enol. If the reaction is under basic conditions, you must show the enolate. Is that okay, everybody? Now, someone has actually also created a slight variation of, let me take this one as an example. They have taken this reaction and varied it slightly, where they added a separate step, and reacted it with, do you guys remember saying? What is it? What does it react as?
A base.
Oh, a base. So what
Takes-
that does, sorry?
No, I was gonna say takes an H.
Exactly. But which H will it take? And it's not a very strong base, by the way. Pyridine is actually not a very strong base, but it's sufficient for this reaction because the product is very stable. The product it will make. It takes it from the beta carbon.
Oh.
Because, and I think you will tell me why is that product so stable?
A conjugate.
Exactly. Conjugation. Conjugation, resonance conjugation causes the product to be pretty stable if a weak base were to take out a proton from the beta position, if that is available, that is. So let me give you some examples of that and see if we can apply it and write the products. But that's only for the acid one, okay? So for example, if what would be the expected products?
Don't you need a halo, the BR? No.
Say again?
The BR gets taken out when you make the double bond.
So it first makes the alpha brominated and then second step is happening.
Oh, that's right.
That's why first step, you'll get this product.
Oh, okay.
Second step, elimination to give us this.
Oh.
Is there another product possible? Comma,
Is there a mechanism to take the BR? Like,
it's like E2. It's kind of, it's, so, okay. Even though it's such a, it's not a strong base, the pyridine E2 kicks out.
got it. Thank
Oh, ha 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 ha. Ha ha, I didn't think about that.
you.
No, really.
So what will be, okay, since that's on the board, what will be the outcome for that one? Can anything happen in step number 2?
No,
So then where will the reaction stop?
it'll stop with the bromination.
Exactly.
Oh,
Because
okay,
there's
yeah.
no beta carbon with hydrogen on it. It can't be the benzene carbon can't do that.
No.
Yeah, so that was on me. That was like, there should be at least a beta carbon. there
One
for
more.
that to happen, yeah. Everybody okay?
Yeah.
Cool. Please tell me. If you have a ketone such as acetophenone, if everybody remembers acetophenone, and I do bromination under basic condition, what will be the product? So the next thing that we're looking for is only for, the next thing we're looking at is only for ketones with a methyl group on the ketone. But anyways, tell me what would be the product? Anybody?
One of the H's on the methyl group is taken out,
Okay, and
replaced with a bromide.
so how about alpha bromoacetophenone?
Alpha bromide.
Right. Is that what you're thinking?
Yeah.
Okay, so how many of you are thinking this is going to be the product? Yeah? And of course, enolate, blah, blah, mechanism and all, we can write. Okay. But there is a challenge here, and this what we are discussing is only for what we call methyl ketones, which means a ketone that has one methyl group on it. This is only for them. Now here's a challenge though for these guys. Are there hydrogens on that alpha position remaining?
Yeah.
Is there still more hydrogens?
Yep.
Okay, so if I were to ask you, which hydrogen is more acidic? The alpha hydrogen in the reactant or the alpha hydrogen in the product? Which one is more acidic?
I would say the first.
So how do we decide which is more acidic or less acidic? We look at the, what do we look at to decide acid strength?
Inductive effect?
Okay, hold on, slow down.
Conjugate base.
The conjugate base. Let's draw the conjugate base. So what's the conjugate base from acetophenone, for example? Do you agree the conjugate base for acetophenone is that guy? Of course it's resonance stabilized because of and make the enolate. Agreed? Everybody okay?
Mm-hmm.
What's the conjugate base from here? Do you agree? Br and minus there. Which conjugate base is more stable?
The second one,
Why is the second one more stable than the first conjugate base?
because the bromine is absorbing the.
So, good. Guys, do you all see that they both have resonance?
Mm-hmm.
Does everybody see that? They both have resonance. They both can do O minus because they both can do that. So that's common. But what does this have extra?
The bromide.
Br. And what does Br do?
It pulls electrons towards itself?
Inductive effect. Does this have the same?
Absolutely.
So then, which conjugate base is more stable? It's this one.
The bromoacetophenone.
So, which hydrogen is more acidic? Is the hydrogen, alpha hydrogen in the reactant more acidic, or the one in the product more acidic? Exactly. And that's the challenge here. Do you agree? Everybody okay?
Mhm.
Why is that a challenge? The challenge is, it is a challenge because what do we have in the reaction?
A base.
So as soon as the product is created, can it exist like this?
No.
As soon as the product is created, what will happen? You said no, so what will it do as soon as it's created?
It will lose the hydrogen.
A proton.
Proton.
React again. You can't stop it because that hydrogen is way more acidic than the original hydrogen. So as soon as that is created, it's seeing a base in the system, it is going to react again and make an enolate again. I'll just use this resonance structure for everybody to see. Agreed? What will that do? As soon as it's created, what will that do?
Get another bromide.
React again with bromine and give us what?
Alpha dibromoacetophenone.
Agreed? Everybody sees that. Does that have an alpha hydrogen still?
Yeah.
What can you say about the acidity of this alpha hydrogen?
Even more stable.
Every time you put a bromine on that alpha carbon or halogen on that alpha carbon, the acidity of remaining alpha hydrogens increases and increases and increases. So can this survive?
No.
No.
This is even more acidic for the same reason as before. So can it survive?
No.
What is it going to do? Well, there's base. Base is going to come very quickly. In fact, this will react faster than that. This will react faster than this. Because you're increasing the acidity of that alpha hydrogen by placing the halogen in that position. Therefore, that hydrogen wants to leave.
Mhm.
Agreed?
Yes.
What will that do?
Another bromine.
Exactly. So the point I'm trying to make is, when you are doing alpha halogenation in presence of a base, polyhalogenation happens. Because we can't stop it. Because every time a halogen is put in the alpha position, it makes any remaining alpha hydrogens be even more acidic than before, which means it will react further and further and further till all alpha hydrogens are exhausted, used up. Everybody okay? Good? So far, do we all understand that? But we've used this to our benefit. We've used this aspect of methyl ketones to our benefit, to actually do something useful. And that reaction is called haloform reaction. In haloform reaction, a methyl ketone, so it is a ketone with one methyl group on one side. So a methyl ketone. If I were to take halogen in excess in presence of a base, so I'm using as much halogen as is needed, what will happen? First, one hydrogen is removed, halogen put in its place, right?
Yep.
But then that loses another alpha proton, another halogen comes in which loses another one comes in. So do you guys agree that this will give us the trihalogenated product?
Mm-hmm.
Is anyone agree with that?
Yep.
But in the haloform reaction, yes, that happens. And then it goes beyond that. It doesn't survive. And I'll write a mechanism. It goes on and creates a carboxylate ion plus C, a haloform like chloroform or bromoform, iodoform, whatever your halogen is, a haloform. That's why the name haloform reaction, because of this byproduct, which is a haloform. Chloroform if X is Cl, bromoform if X is Cl, and so on and so forth. What is this though?
Carboxylate.
And what can we do with carboxylate?
It can receive a proton and become a carboxylic acid.
Exactly. A ketone can be converted into, excuse me, let me say that again. A methyl ketone can be converted into a carboxylic acid through the haloform reaction. Let's look at a specific example and then we'll write a mechanism for that. Let's just use the one that's up on the board there, the one over there, acetophenone. So if I'm using bromine in presence of a base, and I'm using as much bromine as is needed, are you all able to, please, you should show every step. Are you all able to show the steps to convert acetophenone into, right? Deprotonate, make enolate, react with bromine, deprotonate again, enolate, react with bromine, and one more time till all the alpha hydrogens are gone. Are you able to write this mechanism? Everybody okay? Okay. So then let's write what happens after that. So after that, I'm running out of ink. Once that's created, no more bromines can be accommodated because hydrogens are gone. So this is where hydroxide can come in again. But this time, does it have any protons for it to take?
No.
So can it act as a base?
No.
So if not, what else will it choose to react as?
Nucleophile.
Where is the electrophile?
In the middle.
Exactly. There are no more protons for it to take, so it can still act as an electrophile and attack the act as a nucleophile and attack the electrophilic carbon, like we've seen before. What does that do? That creates a tetrahedral intermediate. Have we seen tetrahedral intermediates before?
Mm-hmm.
Yes. What will this tetrahedral intermediate do? There is a leaving group, exactly. That's
CBr
a leaving
free.
group. That's actually a very good leaving group because of the halogens pulling that electron density. That's a good leaving group. So it kicks out the leaving group. What do you think will happen next? Sorry?
What you were writing?
I'm sorry, say that again.
I said that, what you were writing.
Okay, what will happen next?
Would we
Oh,
HOH?
Not
No,
yet.
not quite, no.
Not
What you're
quite-
thinking
not quite
is-
haloform will take
What is
that
this?
proton.
Benzoic acid.
Benzoic.
Acid, right?
Mm-hmm.
Can it survive
No.
if there is a negative ion in the system?
No.
No.
Acid wants to give a proton. It's not a very strong acid, but it's pKa of 4 or something. That's not a very weak acid either. So do you think this can survive with the negative anion?
No.
That's going to take the proton and create what?
Benzoate.
This is where the reaction stops. This is where the reaction stops. So what do we have to do to get that proton back?
Put it in acid.
Acid.
Dilute acid.
Right.
We have to bring in a source of protons to put it back. Exactly. That's the whole mechanism for haloform reaction. First part is on this board where one step at a time, halogen gets put on the alpha carbon till all the hydrogens are gone, and then hydroxide attacks as a nucleophile, kicks out the leaving group, and then the carboxylate ion should get protonated. Make sense, everybody?
Mm-hmm.
Let's do the whole thing one more time. This is called haloform reaction. It is a very useful reaction to convert a methyl ketone into a carboxylic acid. It's only for methyl ketones though. So let's try it out a couple more times. Please tell me the product first and then mechanism. So step number 1 is where we are halogenating. Step number 2, protonate. How about the
And we're gonna write mechanisms
Yes.
for these? Okay.
yeah, please. Do I have any? Yes, please. Mechanism.
Oh,
Mhm.
I can do that too.
So first you have to, using enolates, halogenate on the alpha carbon exhaustively, meaning exhaust all the alpha hydrogens. Once that's done, then hydroxide acts as a nucleophile, attacks the electrophilic C double bond O, creates a tetrahedral carbon, which kicks out the leaving group, which takes the proton from the carboxylic acid. That needs to then be protonated later.
Oh.
You're missing an arrow, Camila, in the first one?
Oh, this one?
Yeah.
Dang it.
It's okay to put a couple of arrows and say repeat steps 1 or 2 or 3.
Oh,
It's okay.
You do the whole thing.
Really? In the
I just
exam?
wanted to see you guys sweat a little bit before I told you.
So in the exam? too?
It's okay.
Oh.
At least if you show one full set. So show one full set and then you can say, step one again or step two again, or
Yeah.
whatever the case might be.
Okay.
So, yeah,
Repeat.
it's okay, because it gets tedious otherwise. Too many times.
Dang it.
So yeah, exactly. The point here is we are exhaustively halogenating the methyl group, sequentially, of course, one step at a time. And then once that's happened, then hydroxide nucleophilically attacks the electrophilic carbonyl. Tetrahedral intermediate kicks out the leaving group. The leaving group is basic and takes the proton from the carboxylic acid. That's where step one stops. So therefore, we need the step two to put the proton back. That's it. Now, I know exactly what you're doing, which is totally fine. Just in case everybody else knows, it is okay to maybe just, say repeats 1 and 2. Repeat steps 1 and 2. What? 2 more times?
Yeah, 2 more
Twice.
times.
Times 2.
Or something like that. Something to the effect where the reader knows, oh, this is happening again, so on and so forth. Or you can do what Dash has done, is actually show out all the steps sequentially to get to the product. Totally fine. Either is okay to do. The point here is iodoform reaction is a neat reaction for methyl ketones only, where this portion becomes a carboxylic acid. So in a way, we've done a substitution on that carbon, if you notice. So this is actually a very, very useful reaction. Any questions for haloform reaction? Okay. Okay, the next reaction, we will not be looking at the mechanism for this one. It's more of a mention and, yep, this happens too kind of situation. It is also an alpha halogenation reaction, which means we're putting a halogen on the alpha position, but it is for a carboxylic acid. This is for alpha halogenation, but for a carboxylic acid. A carboxylic acid that has hydrogens on the alpha position. Again, we need hydrogen on that alpha carbon. This is all about the hydrogen on that alpha carbon. Can be reacted in 2 steps, one with PBr3 in, that's a 3, sorry. 3 with bromine, and then hydrolysis of the byproduct, of the intermediate product, and it creates an alpha bromo product. This reaction, by the way, is called HVZ reaction, Hell-Wohlhart Is there a T? I think there is. Zielinski reaction, hence HVZ reaction. So FYI, we are not looking into the mechanism or anything for this reaction. So for example, oh, I didn't see the heart over there. How many carbons in the heart? How many carbons in a heart?
Two cars. How many carbons in the heart?
You guys go on. You would actually put elbow on the floor. Ew.
What? You.
You wanted to draw the double bond with the heart.
One, two, three, five, six.
Oh, really?
Yeah.
Nice. I need to learn my counting again. Please, let's do these quickly. Please go ahead. Let's do these quickly.
Not everybody else.
Thank you.
Thank you, Sunita.
No, I didn't see that we had to do.
Yeah.
Oh God.
I realize that.
I
Can
don't
we have
read.
the
I don't
answers,
read.
please?
I can't believe I didn't read it. God.
Actually, I didn't even send the, I thought that was it, and I turned the page and I was like,
Oh my goodness.
so I didn't even.
Exactly. How can I even be thinking about that? Can ketones react with Grignards? Yeah, you did it in the lab. Can ketones react with LAH?
Yep.
Yeah, it's a strong reducing agent. Anyways, lessons learned. Let's go do this, please. So what's happening in step number 1?
Step 1 and 2, it's turning it into a primary alcohol.
Steps 1 and 2 is turning it into a primary alcohol because that's anti-Markovnikov. Is
Yeah.
that right? Okay, step 3. What is the outcome of step 3?
Turns an R group into a carboxylic.
It's a primary alcohol, so it turns it into a carboxylic acid. Is that right, everybody?
Oh, that's
Okay,
right.
so what's happening in step number 4 and 5? Anybody?
Adds a halogen.
That's your HVZ reaction. Exactly.
Oh.
That ends up putting a bromine on the alpha carbon, only alpha carbon, so everything else stays the same.
Wait, what's THF?
THF is a solvent used with this guy. It's like ether. THF is basically a cyclic ether, but the point is it's a solvent. That's all we need to know. It's a solvent. It's just dissolving everything.
So just worry
Main
about
part is this
BH3.
guy.
Just
Yeah.
go by BH3.
Exactly. Everybody okay with this?
Mm-hmm.
How do I convert toluene into that shown product?
First step, do NBS and heat.
Okay, so you want to put a bromine on that benzylic position? Okay,
Yep.
good. Then what?
KOT butyl,
Say again?
T-butyl, potassium T-but oxide.
But for what?
Oh.
No, I'm asking, for what? What do you want that to do? I'm assuming you want to do an elimination, but where is it going to eliminate?
Oh,
Can't do
it can't eliminate, so we can't do KOT.
Plus count your carbons, guys.
Mm-hmm.
Do you notice that there's an increase of carbon by 1?
Mhm.
We have added 1 carbon.
CN.
So
Do
that's
cyanide?
1 CN or carbon dioxide. Either way we could go. Either we could go Grignard direction with carbon dioxide or go nitrile direction. Okay. So yeah, we can do a substitution and basically convert this into a nitrile. Okay, then what?
H3O plus heat.
So now you are hydrolyzing the nitrile into carboxylic acid and you added a carbon. Absolutely.
Mhm.
Then what?
Then we do the
BR2,
B-
PBR3, and H2O.
B-
The HVZ, essentially. Dang it.
Exactly. Everybody okay? Carbons, you gotta keep track of your carbons.
Mhm.
Okay, so that is the HVZ reaction. Does anybody have any questions for me? Okay. Next one that we are going to talk about is alpha alkylation reaction of aldehydes and ketones and esters actually also. Meaning we are putting an alkyl group on the alpha position. So do you remember just a short while ago, could we go back to this where I asked you how many enolates can that make?
Yeah.
And you said 2, right? Do you guys remember?
Yeah.
One was the thermodynamic enolate.
The kinetic.
The other was the kinetic enolate. Do you guys remember?
Mm-hmm.
Okay, so, oops, what am I doing? Okay, and we said we need a small base to do this, but a bulky base to do this. And I introduced you to a base called LDA. Perfect, okay. I want to introduce 2 more, which you've seen before. You've seen those before, but you haven't seen them in this context. There are 2 strong but small bases that we have used before. Does anybody remember? So this is strong and bulky. It's a very strong base and it is bulky. But we've seen 2 very strong bases that are actually pretty small. Does anybody remember which ones? Good, that's 1. And? Hydride, very strong, but very, very tiny. So, we can also use these small, strong bases, but that are very, very tiny, to also give us the thermodynamic enolate because they are small. They can go in there and take the more acidic hydrogen and create a more stable enolate. So just please remember them as well. Okay, so the next reaction we are going to talk about is alpha alkylation reaction, meaning that we are putting alkyl group in the alpha position for aldehydes, ketones, and esters. Esters. So, excuse me. Please tell me what will be created if I were to react this. Okay, let's make it a, okay. How about 2-methylcyclohexanone with LDA? What would I get? Anybody?
The less substituted enolate.
So do you mean thermodynamic or the kinetic? Thermodynamic enolate is the more stable enolate. The kinetic enolate is the one that has smaller activation energy for the deprotonation step. So which one is kinetic, which one is thermodynamic, anybody? Which one is this, kinetic or thermodynamic?
Thermodynamic.
Because it's the more stable enolate. Agreed?
Yep.
But this one comes from taking the proton that is more open, so has lower activation energy. That's the kinetic enolate.
So it can. So
which one would I get? Sorry.
the kinetic.
We get the kinetic. Why the kinetic? Why would I get the kinetic as the major enolate and not the thermodynamic? Because, what, say that louder please?
Base is bulky.
Because we have a bulky base. But here's the thing I want to ask you. Is this electron rich or electron poor? Is the enolate electron rich, electron poor?
Rich.
If it's electron rich, what are the two things it can do? React like as a
Nucleophile.
or a
base.
So, if I react this with some leaving group, SN2 happens. You guys remember SN2 reaction?
So long ago.
SN2
When I was
happens,
young.
where this is your nucleophile, that's your substrate, so the nucleophile from the carbon end attacks and kicks out the leaving group. Leaving group gets kicked out. Exactly it's the same thing that we saw in halogenation, except now it's R group as opposed to an X. So what does that end up doing?
That's the R group.
Ends up putting an R in the alpha position. You have alkylated at the alpha position. Do you guys agree? Everybody okay? What if on the other hand I were to use the same, and instead of using LDA, what if I use sodium hydride in the first step followed by same RLG, whatever the leaving group is? Where would the R go? Is this bulky, non-bulky?
Not bulky.
So will it give us the thermodynamic enolate or the kinetic enolate?
Thermodynamic.
So then where would the R go?
On the tertiary.
So we can control the selectivity, the regioselectivity of the alkylation by controlling the size of the base, which decides whether we get the kinetic enolate or the thermodynamic enolate. Does that make sense, guys? Now the important thing here is the second step is SN2. What does that mean? How is that important? What is that? What is the consequence of that?
The enolate is a nucleophile.
Fine, that we know. Why?
R has to be kind of small.
Exactly.
R has to
The
be.
electrophile cannot be bulky because otherwise elimination will happen and you're done. The electrophile for SN2 has to be not bulky. Remember, SN2 is where a nucleophile attacks leaving group leaves at the same time. That means you can't have a bulky electrophile. Make sense, everyone? Does everybody remember that? Cool. Let's try this a few more times then. feel free, come write your answers on the board.
Sure, I got this.
Enolates are nucleophiles. No. Is LDA bulky or not bulky?
Which use pen, Samita?
Bulky.
That's me, what am I supposed to do?
It's bulky.
Yeah,
So then
bulky.
where would the proton go from? Exactly. Is this making sense, everybody? The size of the base will decide which enolate is produced, thermodynamic, which is the more stable one, or the kinetic one, which is the more open one. And depending on the enolate, then that decides where the electrophile would go. So why did you leave the other one? You left it for someone else to come and write it?
Sure,
Because Dash is there, Dash might as well do it.
sure, it's fine.
That's horrible. Is everyone just watching me?
Yes.
Yes.
All eyes on Dash.
All eyes on Dash.
Okay, do you guys agree?
Yeah.
Once again, it's about the size of the base. If it's a small base, we get the proton taken from the more stable position, which means the electrophile goes there. But if it's a bulky base, the proton goes from the more open position, which means the electrophile goes there. Does that sound okay, everybody?
Mm-hmm.
Okay, so same thing here, LDA is bulky, hydride is small. Everybody okay with those two? Now, here, which is actually leading us
No,
to
you're
the
good, I'm
next
sorry.
reaction, this sequence right there. We can start with something and then manipulate it to create a skeleton we need, which is where we're going next. So notice how we started with 3-pentanone and sequentially we added R's, 1 R at a time. Of course, this is symmetrical, so it doesn't matter. LDA deprotonates 1, puts an ET. Ooh, what? Oh, where's what?
No, it's not a double
Where did
bond.
that go?
It's not a double bond.
Where did that go? Yeah, where did you get that from? Oh, I see. No, let's pause. Pause. Okay. So, what's happening in step 1? Do you agree that the LDA is basically creating an enolate?
Yeah.
Doesn't matter which side because it's symmetrical. Agrees?
Yeah.
What's happening in step 2?
An ethyl.
Agree?
Not an ethene group, but an ethyl.
Everybody? Now it's not symmetrical. So now we're using LDA again. Which enolate will be produced? Because now it's not symmetrical anymore.
Mm-hmm.
Will the proton go from the more stable enolate position or the more open position?
Open.
More open.
So the kinetic enolate or the thermodynamic enolate?
Kinetic.
Agreed?
Mm-hmm.
So where will the alkyl group go next?
To that double bond.
So your final product is, so ET went here and the isobutyl. Does that make sense?
Mm-hmm.
I think, oh, for some reason I thought you had a double bond here. Why did we have a double bond?
Yeah, we did.
Okay, anyways, is this okay with you?
Mm-hmm.
Cool. Oh, because that, but then you lost a carbon. I agree that LDA then that, but then did we lose a carbon?
Yep. We lost a carbon.
1, 2, 3, right? And then NH, so this time that's a not bulky base. So where is it going to take a proton from? To create a thermodynamic enolate or to create the kinetic enolate?
Thermodynamic.
So then you get that product. So we are able to control through a sequence of carefully chosen bases, control the position of the alpha alkyl group coming in. Does that make sense, everybody?
Mm-hmm.
Why is this important? Because that leads us to the next section of this chapter. Guys, have you heard of barbiturates?
Yes, I've heard of them.
Yeah, me too. I've never seen them. But the point is, and I've never synthesized them. Lab synthesis of barbiturates actually uses this concept. This idea of creating enolates, depending on where you want to put the R, you choose the base, size of the base, create an enolate, alkylate, and so on and so forth. So that's where we are heading next to understand the importance of this reaction. There are two precursors. What does the word precursor mean, anybody? So something that's used before. Why can't I find my pen? Is this the one? No, that's empty.
Over there.
Where? No.
Not
Anyways.
orange?
No, a black one.
Oh.
Okay. There are two precursors I want to introduce to you which are going to be very important for this discussion. Precursors basically means reactants. So whenever somebody says, what's a precursor to this, meaning what was the reactant for this reaction?
The one before.
So please don't get confused, it just basically means reactant. So there are two reactants that precursors that are really useful for these synthesis strategies. One of them, let me draw them, then I'll write the names. Oops, sorry, wrong. This is called acetic ester. Acetic ester, so the way it's not IUPAC name obviously. This portion is aceto and then this portion is all acetic ester, so to speak. And the other one is very similar to that one, except that it has esters on both sides. This is called malonic ester. It comes from malonic acid, hence malonate ester. These are very, very useful precursors in syntheses using this strategy. The idea here is the acetoacetic ester has two kinds of alpha hydrogens. Do you see that it has these hydrogens, the blue ones, but it also has these alpha hydrogens? Agreed?
Yep.
Can you please tell me, in this example, in this case, which alpha hydrogens, the red or the blue, are more acidic, meaning easy for the base to take?
The ones in the middle.
Why?
Stabilized by resonance.
Louder, please.
Because it's in the middle of the two oxygens.
So,
Stabilized by resonance.
On both sides.
Yes.
Exactly. Once you get a negative charge here for the conjugate base, that negative charge can be delocalized here, but also delocalized there. Can you all picture that in your minds? So the conjugate base from here is very stable. But which hydrogens are easier, faster to grab? Not easier, that's the wrong word, because easier means stability, faster means kinetics. Which ones might be more open for the base to take?
Those,
Right?
The
Because
red.
they are not hindered by sterics or anything, so they are more available, more open, more accessible. So that's the kinetic situation, this is the thermodynamic situation. Everybody agrees? But malonate ester has only one kind of protons that can participate in this reaction, which are those, and they are very acidic, very acidic. So, here is how we use one or the other. Let me show the outline for both. We'll try and grab the idea, then we will practice it.
Sumita,
Yes,
this might
please.
be a dumb question, but why
Yes.
don't we have the one on the very end?
But
not drawn out?
what is being dropped? Is it me or is it you?
It's me, I'm sorry.
Oh, okay, you.
I'm sorry.
Say that again, Jane.
If you drew out the ethyl, there's hydrogens on those.
But are they alpha to the
Okay,
C
yeah,
double
yeah,
bond
that's the
O?
answer.
No.
Thank you.
Right, that's the idea basically. It's the hydrogens on the carbon alpha to the C double bond O. That's it. Nobody else. Okay, so let's start with acetoacetic ester first and see how can it be used to create different kinds of syntheses. Now, again, since there are two different kinds of hydrogens, we can control which ones are going to be taken by the base. If we use a bulky base, this one, these get taken. If we use a small base, those ones are taken. Same thing. So, I could, if I use a bulky base, I could create a more stable enolate, right? Would I use a bulky base for that or a non-bulky base for that? For this one?
a small base.
Do you all agree? Or I could create this enolate. And this one would need bulky base. So I would use LDA for that because I want this, but I need a small one, which means hydride or amine, whichever one, those are small. Or because those are so acidic, these are very acidic hydrogens because they're surrounded by two, we can also use, and in fact that's what we will use most commonly, is ethoxide, because hydrides and amides could do something else that we didn't intend to happen, so let's just do ethoxide, and that's going to be, give us the thermodynamic enolate, not the kinetic enolate. Now, why am I underlining that? Because the RO minus matches whatever this is. Otherwise, again, something else might happen that we didn't intend to happen, so that keeps things clean that way.
But if,
Yeah,
if
sorry.
we use H, it would just be H.
I would actually, these are not going to be used as much in this synthesis. It will probably be ethoxide to get that.
Okay.
But now what do we do? Let's just take one track, because it's the same for all tracks, if you understand that. So now I can use an alkyl group. I can alkylate on the alpha position. Agreed? If I needed, again, if there is a need, depending on the synthesis, we can use ethoxide again, followed by a different alkyl, which means I can do a double substitution. Again, it depends on what is it that we are trying to make. I can, right? If we need it for the synthesis, I could then deprotonate here, put R's over there, whatever it is we need to do. We can manipulate the situation based on that. Everybody okay so far? Once you've done whatever R's you need to put, once you've put all the R's wherever they need to be, now we hydrolyze the ester. Please notice that's an ester. If I hydrolyze it, either saponification or acid hydrolysis, whichever method, what does that do? It converts the
ester into
into a
carboxylic acid.
Everybody okay? Now that's a special carboxylic acid. That carboxylic acid is a beta keto acid. What does that mean? Let's process it. This carboxylic acid has a keto group, C double bond O group, in the beta position. That's alpha, that's beta. Here is your beta keto. So these are called beta keto acids. You all see that structural feature. There's a C double bond O, beta with respect to the carboxylic acid group. Now why are they so special? Beta keto acids, if I heat them, just heat, they undergo decarboxylation reaction. They lose carbon dioxide very spontaneously with heat. Now please, let me show you where. Where is the carbon dioxide? So if I heat this, it loses carbon dioxide. If it loses carbon dioxide, that's called decarboxylation. What does it leave behind? Anybody?
A ketone?
Exactly. Where did that hydrogen go? That basically attaches to the alpha carbon. So the hydrogen comes here, R, alkyne, ketone. Carbon dioxide's gone. So if I use this guy as my precursor for the synthesis strategy, I am able to create what I like to call substituted acetone. And again, you can put groups whatever you need to depending on what is it you're trying to make based on our planning. And we'll do examples, lots of examples for these syntheses. So that's for acetoacetic ester. What about malonate ester? Same idea, same thought process, same strategy. So if we start out with malonate ester, and we use a base and then Rx. Maybe again, if we need, we use the base again, and Rx again. Again, it depends on what do we need to do. We can put R's here. Agreed?
Mm-hmm.
Now, whether you need 1 R or 2 R's, that again depends on what is it we want to make. But we get to that point. After that point, we can hydrolyze this. Again, we can either hydrolyze it with acid or saponification. Saponification is, please remember, it's base hydrolysis, hydrolysis. Whichever method. But what does that do? Anybody?
Makes it a dicarboxylic acid.
Exactly. Both esters are hydrolyzed into carboxylic acid. Again, this is not an ordinary carboxylic acid. It is a beta keto acid. Because if you look at one carboxylic acid group, there is a C double bond O in the beta position. If you just focus on one carboxylic acid, whichever one, it doesn't matter. If you focus on one carboxylic acid group, alpha, beta, there's a C double bond O next to in that beta position. So this is also a beta keto acid. All beta keto acids undergo decarboxylation, meaning lose CO2 when heated. Can someone tell me what would be left behind if this undergoes decarboxylation? Say again?
A alkane.
No. And I think that's I asked you that question because that's the answer I was expecting to get. So guys, how many CO2s would it lose?
Two.
Careful.
Oh,
One.
one.
Because if when one is lost, let's say this is lost, do we have a beta keto acid anymore? No. As soon as one CO2 is gone, let's say, do we have a beta keto acid anymore?
No.
So it can't do this again. It loses only one because it can only happen for a beta keto acid. It cannot happen for any carboxylic acid. So how many does it lose? It loses only one. Can't lose two. Just because there are two, it can't lose two. Let's say that one is lost. What is left behind?
The two R groups, the hydrogen and a carboxylic acid.
Agreed?
Mhm.
I call this a substituted acetic acid. Because that portion is acetic acid, we are putting R's on the alpha carbon to create the product. So, depending on what is the product we need, we either start with this precursor and strategically plan out our reactions, or start with this precursor and do the same. But do we all understand the basic idea? Okay, so let's at least try and look at a couple of specific examples, and then we'll do more as we go through, because this is a very important topic. So let's say I'm starting with malonate ester. What will that give us? Step by step by step. Can I erase these two general outlines or leave them?
Where?
Go ahead, meaning erase them, it's okay? Cool, okay. Let's try that, please. So one step at a time.
Four.
Rita,
Yes,
is the heat from step 6 carried
same,
over? Okay.
exactly. You can combine those, exactly. You could take the heat and, when you're heating, it's doing both.
Okay.
Exactly. we will continue this reaction again on Monday. This will not be on the exam. The exam is on Tuesday, like planned. We can't change it. So this acetoacetic ester and malonate ester synthesis will not be on the exam next week. But because we are not done, we need to do many more examples of this too.
So just these last two won't be.
Yeah, those won't be on the exam.
So the second exam covers all the content from,
It's the second half of aldehydes, ketones, and then carboxylic acids and derivatives.
okay, everything since the first exam up
Mhm.
until this past Monday,
No, even something today, except
Oh, yeah,
from
up-
this reaction.
up until,
Yeah.
huh?
Yeah.
Thank you.
I like this, can we do this meeting?
I like it too, but we need to do more examples. I think you added carbon.
Yeah.
Don, keep track of your carbons, guys.
It's gonna go too.
I was trying to look at those reagents.
I think you lost it. So what I like to do when I do these ones is I circle the part. So since this is the reagent I'm using, this that's the portion I will keep, right? This is the same. So we brought in that group counting your carbons, and we brought in this group counting my carbons. So this carbon is that one.
I made sure to count them, and that was why I was mumbling like.
Yeah, no, that's all. Yeah.
Yeah.
Count your carbons.
It doesn't label it.
What's the problem?
Where this goes?
Where does that go? Your answer is absolutely correct. Let's quickly go through these guys because we are out of time. Okay, can we do this quickly?
Yeah,
You
yes.
guys all agree?
Yes.
Everybody okay?
Mm-hmm.
Do you guys agree? Again, notice how you can control the size of the base and the strength of the base also. So, do you all agree? So this carbon right here is actually that one. Everybody okay with that?
Mm-hmm.
Now here we changed the base. So that one deprotonated on the other side. So this carbon is that one. And this carbon is this one. Am I doing that correctly? Because LDA is the bigger one, it deprotonates on the end. Everybody okay?
Mm-hmm.
What's going on here, guys? Very quickly.
No idea.
So, what's the first step?
First
LDA, is that going to deprotonate on the terminal or the internal?
Terminal.
terminal.
Okay, good. Very quickly, I promise you. Okay, what's happening in step 2? Where is the alkylation? Agreed?
Yep.
But notice there are 2 bromines. How many okay, I don't know how to say that correctly. How many substitutions would happen? One. There's only one nucleophile. So, 1, 2, 3, 1, 2, 3, and bromine.
Yeah, and it beat
Right?
from. Yep.
Okay, what's happening in step 3? I do it really bad.
Another deprotonation.
But where? From where? Is it
On the-
deprotonating here or inside?
Inside.
Because that's a weaker base, so that's the more acidic hydrogen. So it's creating an enolate, but it's creating it on the inside alpha carbon. 1, 2, 3, 4. Agreed?
Mhm.
1, 2, 3. What's going to happen next?
The OET.
Substitution.
Lovely.
So in this step, because it's an intramolecular SN2, there is a leaving group situated in the right position for the nucleophile to attack intramolecularly and close the ring. When you close the ring, how many carbons in the ring? 1, 2, 3, 4, 5, and 6 carbon ring. So you create a cyclohexanone, but we also have that thing,
So it'd be a cyclo.
right?
Oh.
So what's happening in step 4? You asked me where is the ethyl group? Where is the ethyl group? When that hydrolyzes, it becomes a carboxylic acid, right?
Mm-hmm.
But that's a beta keto acid. And you're heating it too. So what happens to the beta keto? Well, what happened to the ethyl? It becomes ethanol. Not plus, minus. I mean, we've written the mechanism of hydrolysis of ester kicked out.
Mm-hmm.
You see that? And what's happening here? Decarboxylation. So you close the ring, and this is why, and we'll do more examples, guys,
Wow.
next week. We'll do many more examples of that kind too to get a good idea. So exam on next Tuesday will not cover this synthesis, but will cover everything till then. But Monday we don't have a quiz then, am I right?
I hope not.
Because we have an exam on Tuesday. So cool, then we'll finish this part and more on Monday. Again, my goal is to finish these 2 chapters next week, so let's see, hopefully we can. Yes,
I have a question.
please.
So I was looking at my test.
Oh, let's see, what did I take some more?
Right.
Yeah, what did I
I
do?
was noticing these 2 answers are the exact same.
Oh, I'm not reading properly. I'm not reading properly. Yes, hers is wrong. Yes, yes, yes. No, hold on, hers is not here. No, yes, hers is wrong. You're right, sorry. Yes, where's the pen?
Tomorrow.
Yeah, because you can't, the ketone can't be reduced with this.
I did.
That's why it stops at the alkylation stage, right? Otherwise it would. Thank you. Yeah, I just like her better than you. What can I do, check? What am I?
Okay.
Study at Starbucks?
No, you're right.
Well, we have a Starbucks
But then,
by my house.
this
and
too then, this is wrong too.
It's just vegan, really healthy. It's very convenient.
Let me just make sure.
Okay,
Yeah,
so study
you
at
get a ketone,
Starbucks
but
then?
ketone can't react.
Well, unless you're coming, let's see if I'm yes.